So today's talk is by Souradeep from IISc. Uh, I guess you can start now.
Okay, so I'm Souradeep from Indian Institute of Science, and I'll be talking about neutrino oscillations. So let me share my screen first. Can you see my screen?
Yes, it's visible.
Okay. So I'll be talking about neutrino oscillations. It is a it is an astronomical phenomenon which can be explained using some simple rules of quantum mechanics and some high energy physics. So this is the outline. I'll be giving a brief introduction about the topic in general, and then I'll be moving to a theoretical model by which you can describe neutrino oscillations. Then I'll be showing two approaches to understanding how neutrino oscillations occur. So first will be the wave function, and second will be density matrix approach. So let's begin. Neutrinos are the lightest class of particles. Actually, they are the lightest class of fermions, and they are proposed under the standard model of physics. Now, they were first introduced by Pauli, and it was because there was a violation of the law of conservation of momentum in the process of beta decay. So, what is beta decay? It is a process in which a neutron decays and gives rise to a proton and an electron. It was believed earlier that only proton and electron are the end products, but it was so found that a proton has a spin half and an electron also has a spin half. So two spin halves cannot add together to give a spin half. So we know that the neutron has a spin half, proton and electron both have spin halves. If we add two spin halves, we'll get a spin 1 and a spin 0. We cannot get any spin half by using two spin halves. So we'll need a third particle with a spin half. Otherwise, the law of conservation of angular momentum is violated in this case. Also, it was found that the total energies are quite different. Like the initial total energy and the final total energy are found to be different if we do not consider a hypothetical new particle. So this particle was the neutrino, and I'll tell you some properties of the neutrino. It has a spin of half, and under the standard model, it has a mass of 0, and it also interacts very weakly with matter. Like uh, there are trillions of neutrinos passing through your body each second, and we cannot detect those. So let me discuss two aspects here: mass and flavor. So in the standard model, neutrinos are assumed to have 0 mass, and any particle with 0 mass can travel at the speed of light. So neutrinos are relativistic in the standard model, and there are three flavors of neutrinos. So in the standard model, there are three kinds of fermions, and there is a corresponding lepton to a corresponding neutrino. For example, there are three classes or three flavors of fermions called electrons, muons, and tau particles. And similarly, there are the anti-electron, anti-muon, and anti-tauon, where anti-electron is called a positron. Corresponding to each of the leptons, there is a corresponding neutrino and an anti-neutrino. So there are nu e, nu mu, and nu tau, and these antineutrinos nu bar. Now, why do we need to have neutrino oscillations? That is because there was an astronomical problem. So in the sun, the proton-proton chain produces a huge number of neutrinos, and there is a standard solar model which could explain all the properties of the sun, for example, the neutrino flux and etc. So uh, there was an experiment carried out in the late 1960s by two scientists, and it was called the Homestake experiment. It it was actually detecting and counting the solar neutrinos. And from this experiment, there was a measured rate of solar neutrino flux and a theoretically derived rate of neutrino flux. But there was a discrepancy between the two values. The observed flux was just one third of the theoretical flux. So, in order to explain this, only a particular model, which is called the neutrino oscillation model, could be uh, successful in establishing this discrepancy, like to resolve this discrepancy. Now, actually, the origin of neutrino oscillations was way before that. In 1957, a scientist, Bruno Pontecorvo, he uh, postulated that there should be some oscillations of neutrino, and this oscillation is actually an oscillation between different flavors. So, for example, if you start with an electron neutrino, now you don't actually start with a single neutrino, you start with a wave. And there is the wave matter duality, which means that, uh, sorry, the wave particle duality, which is just a way of looking at quantum field theory where particles are the excitations of waves, or particles are the excitation of fields. Now, uh, so a neutrino can be described by using a neutrino field, and the neutrino particles are just some ripples inside that field. Now, if we start with with an electron neutrino wave, after some time it oscillates and turns into a muon neutrino wave or a tau neutrino wave, and it oscillates back and forth between that. So how can this solve the solar neutrino problem? This is because we are saying that the sun, it produces only electron neutrinos. That's because uh, the natural source of electron neutrinos is by the beta decay. Now, uh, beta decay of a proton gives rise to a neutron, a positron, and an antineutrino. And beta decay of a neutron gives rise to a proton, and electron. Sorry, sir. Uh, the neutrinos are produced in the beta plus decay, and antineutrinos in the beta minus decay. So, just like the electron flavored uh, decay, like decay of electron, when the electron is produced in the decay, it gives rise to a neutrino. Similarly, when muon is produced in the decay, it gives rise to a muon neutrino, and so on. Now, muons and tauons are quite rare compared to electrons. So the sun doesn't produce so much of muon or tauon neutrinos. Now, you start with a wave which is completely consisting of electron neutrinos, and after some time it oscillates to muons and tauons. So as a result, the proportion of electron neutrinos becomes very less. And since we can detect only electron neutrinos, we count only a fraction of the initial neutrino flux. And that explains that the solar neutrino problem is actually because of neutrino oscillations. Now, how do you describe it theoretically? So neutrinos have two main properties which uh, concern us here. The first is its flavor, and the second is its mass. So, neutrinos can interact only through weak force and gravity. When it interacts through weak force, it has to interact with the particle. So it can either interact with an electron or a muon or a tauon. And depending on which kind of particle it interacts, it collapses into a particular state. And sorry, it doesn't depend on the type of particle it is detecting with, but it collapses into one of the states whenever it interacts by weak force. And we can only detect the flavor of it. For example, if we put an electron neutrino detector and pass some neutrinos through it, it will tick only when an electron neutrino passes through it, or it will tick only when the neutrino that passes through it, it collapses into an electron state. If it collapses into a muon state, it will not tick. So it is kind of a measurement. We measure the flavor of the neutrino wave. And as you know, there is a basis called the flavor basis. So a neutrino wave is a sum of three basis vectors with some
Excuse me,
coefficients.
Souradeep.
Yeah.
Yeah. So, like when you say when neutrino is detected, it randomly collapses to one of the three flavors. You mean
Yes.
it collapses when it is detected, like before or after, like that? Like, yeah.
No, it
You understand my question?
just at the same time. I think the time difference doesn't make any like it doesn't make any difference here.
It doesn't make any difference. Then, I mean, like it can, if it collapses after it is detected, it can also take that.
No. Uh,
Yeah, exactly.
what do you mean after it is detected? Like whenever you detect it, it you
You
cannot
mean
detect the
the
mix.
collapse? You mean the collapse phenomena is due to the detection?
Uh, you cannot say one thing is due to another thing. Like they are just uh, see collapse and detection. They take place at the same position.
At
So
the
I
same
don't
time, right?
think
Right.
yes, I don't think you have much difference of time
Okay, it
between
is
those.
some kind of that measurement operator or something. Right.
Yes, yes, it is actually a measurement. It is a quantum measurement
Oh,
process going
obvious.
on.
I see. I see. Oh, then collapse is obvious, right? Yeah.
Yeah. So it collapses
Okay.
into either of the three states. So
All
if it
right.
collapses into a new E state,
Right, 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 right.
it
I
will be
got it.
detected as an electron neutrino. Okay. So now you can see the coefficients are there, and these coefficients actually are the probability amplitudes. So if you take CE and if you look at the probability of detecting new E, so you know what is the measurement postulate of quantum mechanics? We measure, and after measuring a state, it collapses into one of the several basis states with a certain probability. The collapse is random, but the probabilities are known. So the probability that it will collapse into new E is mod CE square. Similarly, for new mu is mod C mu square, etc. Now, that was about when a neutrino interacts with matter. But most of the way, a neutrino travels just free. It is like a plane wave in vacuum. And for a plane wave in vacuum, you know that uh, the energy is given by the relativistic formula for energy, root over p square plus m square. Now, I will explain this subscript I later, but now imagine if p is much larger than m, that is the ultra relativistic limit. Just like what we do in the non-relativistic limit, we get that this thing is equal to m plus p square by 2m by doing a binomial expansion up to two terms. Similarly, we can do a binomial expansion by taking p square common here. Then we get 1 plus m square by p square and take a root of that and multiply with p. You will get this expression. This is when p is much larger than m. Now, you know this when E is much large, we can consider E is almost same as P because the second term is quite small. Now, if we assume that P is almost the same for any neutrino, then uh, the entire energy will be just uniform but slightly different from uniform depending on the mass of the neutrino. Now, suppose we are considering that it has some mass mi, like there could be different masses of neutrinos. So the ei of the ith particle will be mi squared by 2p plus this constant factor of p. Now, this was actually the assumption that every plane wave, like a neutrino, is traveling as a mixture of three flavor waves. But you can also write it in another basis, which is the basis of mass. So in that basis, there are just three basis states. So the basis number of basis states has to be conserved. But here the basis states, each of the
why are you considering P as a constant here? Why not Pi?
I'm considering that the neutrinos are at the same energy, like it is a monochromatic beam.
Monochromatic beam, then it is EI, right? So yeah, so like
Actually, it doesn't matter.
actually it
There is
doesn't
a
matter, yeah,
slight
right?
difference.
Because
Yeah,
anyways, EI, the difference between EIs is very small. That's why.
yeah.
Yeah, okay.
So actually, the p is constant here, and m is a variable, which we'll see that it is different for three different basis states. I'll explain it later. So uh, each plane wave has a different mass, but they have the same momentum. By momentum, I mean the three momentum or the Newtonian momentum, I guess. Actually, it's not the Newtonian momentum here. This p is related to the frequency of the wave. If you consider it as a wave. Now, I have assumed here that neutrinos have mass. So this is a deviation from the standard model, and we are assuming that uh, it is allowed to have a mass of neutrinos. Now, these mass eigenstates, what are the mass eigenstates? So I'll explain to you. When a neutrino interacts with matter, it is in the flavor basis. So when it interacts with matter, it collapses into one of the three flavors. But when it travels freely, it is in one of three other basis vectors. That is, uh, just consider it as a rotation. For example, we can use the Cartesian coordinate system, which is x, y, and z. But you can also use the spherical coordinate system. The number of basis vectors is the same. Here it was x, y, z. Here it is r, theta, and phi. But uh, the coefficients are different and the interpretations are also different. So similarly, the flavor basis and the mass basis are just two different bases of it. And since they are two different bases, we can relate them by some unitary transformation. And this transformation is known as the PMNS matrix. So here, each of the three eigenstates that the neutrino uh, assumes when it passes through free space has a different mass. So here I can be 1, 2, 3. Similarly, there are M1, M2, and M3. There are three different masses of the neutrino, and hence three different energy eigenvalues. Now, these two eigenstates are not the same. So when they travel freely, it is in the mass basis, and when it interacts through weak force, it is in the flavor basis. Actually, at any time we can represent it by either mass basis or flavor basis, but it turns out that it is more helpful or more convenient to use it in the particular basis. That is because the free particle Hamiltonian depends on the mass, and the interaction Hamiltonian, or when it is interacting, the Hamiltonian depends on the flavor. That's why we always prefer to diagonalize the Hamiltonian. That's why we're using two different bases at two different situations. Now I'll describe the theoretical model. So we start with the general state of it's a quantum state of the neutrino wave. Since the basis is three-dimensional, so we'll be using three coefficients here, and everything depends on space and time. So this C1, C2, and C3, they are in the mass basis given by subscript M. So consider the basis state 1, 0, 0. So C1 is 0, C1 is 1, and C2 and C3 are 0, which means that the state is purely the first basis state in the mass basis. So if you somehow measure the mass of the neutrino when it is in the state 100, you will measure it as m1. Similarly, the state 010 will have a mass of m2, and the state 001 will have a mass of m3. And we just assume that they are in the ascending order. Now, we can also represent this in a different basis, which is the flavor basis. So just consider this as representing a three-dimensional vector in the Cartesian coordinate system and the spherical polar coordinate system. It will have different components here, and we can actually relate those components. So here C, E, C mu, and C tau. So for example, in the flavor basis, a neutrino which is 100, it is a purely electron neutrino. And the PMS matrix, which is denoted by
Souradeep?
U. Yeah.
Yeah, so can you go to the previous slide?
Yeah.
Yeah, so how do we actually know that this mass and flavor, these two are two different bases and not two different quantum numbers that we can write the state as the cross product of these two things?
I think that's because you cannot measure the mass and flavor at the same time.
Uh,
So
yes.
it is kind of two different, say, two different directions of a spin. So for example, you cannot measure SY and SZ at the same time.
Right, right.
If you could measure them, then they would be the same basis or a cross product of them.
Right, right. If they are measurable at the same time, they will have the same eigenstates
Yes,
also.
and you will not observe neutrino oscillations in that case.
Right, right, right.
So U is the matrix that relates the two basis states. So here are some numbers, here are some numbers, and U is the matrix that relates the two vectors here. Now, it is from the general considerations of quantum mechanics that U must be an unitary matrix. Now, what are the components of U? So it is actually easy to represent the matrix U by using three parameters of this. Sorry, it should be four parameters. So there are three mixing angles. I'll tell you what the mixing angles are in a moment. And there's a phase angle delta Cp, which is related to some symmetry violations. Now, although there are many other ways of parameterizing the matrix, we are just going to use one specific parameterization. Now, uh, so you know about SU3. If you just you have not heard of this before, just you can just ignore this part. SU3 is a special kind of matrix. It is a unitary matrix which is having it's a unitary 3 by 3 matrix which has determinant of 1. It is actually described by 8 real parameters, but here we are using 4 parameters. I will tell you why it is 8. That's because, see, a special unitary matrix. Unitary matrix means it is its inverse is its Hermitian conjugate, and it is a complex matrix. So the entries are complex numbers. There are total of 9 entries, which are complex numbers, which means that there are 18 real numbers. Out of those 18, we can actually make them half because we are using the condition that u inverse equal to u dagger. So it becomes 9, and then you just make its determinant equal to 1, which reduces another one parameter. So there are 8 real parameters, but we are using here 4 because there is a symmetry in quantum mechanics, and it says that a global phase doesn't matter. So just take a quantum state and multiply it by some e to the power I theta, where theta is a real number. Then the resultant state and the previous state are physically the same. So that removes some of the parameters, and we can just use 4 parameters. Now, U is written as a product of 3 other unitary matrices, and these unitary matrices are rotations along 3 axes. So this is a rotation about U23 is a rotation about x axis. This is about the z axis, and this is about the y axis. But this is not exactly a rotation because there is an extra phase added here, the delta Cp, and here a minus I delta Cp. Now these have been determined experimentally, and these are the values. So you can see that thetas, the mixing angles, are determined to very good accuracy, reasonable accuracy, but delta Cp has a large uncertainty in it. But if there was no charge parity symmetry violation, uh, we would uh, we would expect that delta Cp is 0. But currently the measurements or observations suggest that this is the range of delta Cp, which is close to 180 degree. Now I'll describe how I have so I have made some plots which describe the neutrino oscillations. I will explain here how these plots I have made. So first of all, we have to define the PMS transformation U, and I have already shown how to define this transformation here. And first we start with the state vector, which is in flavor basis. So say you are starting with a purely electron neutrino. So in the flavor basis, the vector will be 1, 0, 0. Now you convert it to the mass basis. How do you do that? You just multiply it by U inverse. And that is because uh, the flavor vector is U times mass vector. So the mass vector will be U inverse times the flavor vector. Now, after you have it in mass basis, so the mass in the mass basis, the Hamiltonian is diagonal, and its diagonal entries are p plus m1 square by 2p, p plus m2 square by 2p, and p plus m3 square by 2p, where m1, m2, m3 are the 3 masses of the 3 mass eigenstates. So you can evolve it. How do you evolve it? Just multiply each component of the vector by e to the power minus EIT by h bar. That is the simple rule of evolving in quantum mechanics when the Hamiltonian is diagonal. And then you can transform it back from the mass basis to the flavor basis. And you will have a vector which is in the flavor basis. So there will be 3 components of it. And from those 3 components, you can determine the probabilities. How do you do that? That's because you have 3 components here at later time t, and these components will be, say, there are some 3 complex numbers. And if you take the mod square of any component, you get the probability of the neutrino being in that particular flavor. Now, it is important to notice that the actual masses do not matter here. This is very similar to the concept that the actual energies do not matter, but the differences in energies are important. So similarly, since the energy actually depends on m squared by 2p, the mass square differences. So, for example, m1 square minus m2 square, m2 square minus m3 square, these are actually the important quantities and not the actual masses. Now I have used the following parameters. As you can see, delta Cp is very close to 180 degree here. And it is also important that delta Cp is not accurately determined. There is a large uncertainty, as you saw, 42 degree on the top and 25 degree at the bottom. Now, I had to assume something for the masses, so I assumed that M1 is 0 electron volt. So masses we represent as electron volts because uh, we can convert mass to electron volt by using Einstein's formula. So E equal to mc square, and you just multiply the mass by c square. You will get it in joules, and then you divide it by the charge of an electron numerically. So you get that same numerical answer in electron volts. Now this delta m12 square, which this actually means m1 square minus m2 square. Similarly, this means delta m13 square means m1 square minus m3 square. Or sorry, it is actually m2 square minus m1 square and m3 square minus m1 square. And p I have assumed to be this, but it doesn't matter here. So I have plotted this using a code, and here we are starting with the initially electron neutrino state. So you can see that the probability of nu E here is initially 1, and the probabilities of nu mu and nu tau are 0. As time progresses, the oscillations take place here, and after some time, a large part of the neutrinos are converted into muons and tau neutrinos. So this can explain the neutrino oscillations or the solar neutrino problem. So just consider we are observing this at this point of time. So we'll see a lot less electron neutrinos than which were produced from the sun. Now this is actually an oscillation because if you plot it for a long enough time, you'll see that it is undergoing uh, this kind of wave emotions with some smaller oscillation imposed on the larger oscillation. Now, there we had considered a particular value for P or a particular value for E, but we can reduce the dependence on it by just dividing the time by E. And it makes the plot independent of what energy we are using. So why did I use this quantity and these units? It is because I was reading an article on Wikipedia and they had some similar graph. So the main idea that I used for this entire thing was I was reading an article on Wikipedia about this neutrino oscillations and I saw this graph. So I tried to reproduce this graph and finally ended up making this presentation. So there they had used these units L by E. So I just converted this and this actually makes the graph independent of E. Now, instead of starting with a completely electron neutrino, we could start with a muon neutrino or a tau neutrino. And you can see a similar kind of oscillation here. Now, let us see what are some of the interesting observations here. So, let's see. If you look back, you'll see a small amount of neutrino converted into muon or tau when we started with purely electron neutrinos. As opposed to it, when we started with a purely muon neutrino, it gave rise to a huge amount of tau neutrinos. As you can see in the graph, the tallest peak of tau is above 0.9, while the tallest peak of E is around 0.6. Similarly, if we start with the tau, the tallest peak of mu is around 0.9, while that of E is very low. when you started with an E, the tallest peak of mu and tau were very low, around 0.5. And you can also, you may have also noticed that these are just alternating. Mu and tau are just alternating between them. Like after every mu wave, there is a, so after every peak of a mu wave, there is a peak of a tau wave here. And this is because they are strongly coupled to each other than to the electron neutrino. And this is not exactly the particle physics kind of coupling. This is the coupling between the uh, two states in the Hamiltonian. So we have seen it the Hamiltonian. The Hamiltonian is diagonal in the mass basis, but if you convert it to into the flavor basis, it no longer remains diagonal, and there will be some off diagonal terms. Now the off diagonal term between mu and tau is large, while the off diagonal term between mu and e and tau and e are small. Also, you can notice some beats here. There is a large low frequency mode and a small high frequency mode here. And if you can count this, you will see that. So suppose we are starting at 0 and counting up to say 35,000. It is approximately one wavelength of a large wave. If you count, you will see there are approximately 30 wavelengths of the high frequency mode here. And this 30 actually comes from the fact that the ratio of the two quantities, m3 square minus m1 square divided by m2 square minus m1 square, is approximately 30. Just look at these numbers here. The ratio is around 30. So that is what gives rise to the high frequency and low frequency modes. Now we'll look at the same thing using density matrices. But why? So, you know, uh, wave function can be used to only represent a pure state. You cannot represent a mixed state by this. What do I mean by mixed state? So, a pure state is much like a polarized light, plain polarized light. You can represent a plane polarized light by a single vector, which is the plane of the polarization, which is along the plane. But if you want to represent unpolarized light, you cannot just uh, write a wave function for it. It is there are many standard examples which show that uh, a mixed state like unpolarized light or even partially polarized light cannot be described completely using a wave function, and hence you have to use something called a density matrix. It is much related to statistics as well. So a density matrix is just the wave function with its dual vector. If you just arrange them in the opposite order, like keeping the bra first and then the kit, then you would just get one. But if you first keep the kit and then the bra, then you will get some matrix. It will be a 3 by 3 matrix if the vector is three-dimensional. So that matrix is called the density matrix here. Now, we can use a density matrix to explain or to describe a mixed state. Now, you remember there was a transformation formula for the state vector between mass state and flavor state, or sorry, the mass basis and the flavor basis using a single U matrix. This is the formula that we're using. So psi in the flavor basis is U times psi in the mass basis. But here we have to use two U's. That's because just uh, just look at the formula for rho here. If you put U before this psi, you need to put a U dagger after this psi, so that everything remains consistent. And that's how the U dagger comes after the rho m. And just like the evolution of a state wave vector in the in quantum mechanics, this formula is used for the evolution of the uh, density matrix. And this is actually valid only when the Hamiltonian is time independent. Otherwise, you have to consider many other factors, and it is complicated in that case. So for time independent Hamiltonian, this is how the density matrix evolves in time. And how do you do the calculations in this case? It is very similar to the wave function approach, just we need to change some formulas. So as you can see, the steps are quite similar. Just in step 2, we start with the density matrix. In step 3, we use this formula to convert the density matrix from flavor basis to mass basis. Then we evolve it just like we did in the wave function formalism. And at last, we convert the density matrix into the flavor basis. Now, I would like to tell something about the evolution. I'll do it later. But how do you interpret the density matrix? So we know how to interpret a wave function. We just uh, consider a particular coefficient of the vector, and mod square of that coefficient gives us the probability that the particle will collapse to that particular basis state. For density matrix, there are for this case there are 9 elements. How do we interpret this result? So in density matrix formalism, uh, we can similarly describe the expectation value of any quantity. And for that, we use this formula. It is the trace of rho times the operator. Now, what is the operator that we want to measure here? The operator is actually a projection operator on the flavor state. So, for example, if you want to measure the probability that it's an electron, so just consider in the wave function approach. Suppose you have a wave function that is say it is Ce C mu C tau in the flavor basis. So what is the probability that it is in the electron neutrino state? The probability is Ce mod squared. Now that can actually be written as uh, that can be written in the bracket notation using uh, the wave vector, the dual wave vector at first, then some matrix, and then the wave vector. Now, you can easily see that if we use this matrix in the middle and put the dual wave vector at the left and the wave vector at the right, and we just multiply to get a number, that number will be mod c square, mod ce square. Similarly, if we just make this matrix 0, 1, 0, so the middle element here is 1 and all the other elements are 0, and then we put the dual vector at the left and the vector at the right, and we multiply it again, you will get mod of c mu square and so on. Now just consider that this is the projection. This is called a projection matrix. So it actually projects the state from any general state to a state which is a purely electron state. So you can just apply this matrix on the uh, column vector, the state vector, and the resultant vector will be a purely electron neutrino state. Now, what do you get if you take a trace of this thing? So O is this matrix, this projection matrix, and rho is the density matrix, any general density matrix. You can show that this probability that you get from there is just the first diagonal element of the density matrix. So a density matrix is 3 by 3, and there are three diagonal elements in there. The first diagonal element gives the probability that it is in the electron neutrino state. The second gives the probability of being in muon neutrino state, and the third one gives the probability of being in tau neutrino state. So after we evolve the density matrix, we can just look at the different diagonal elements and interpret them as the probabilities. But how do we evolve the density matrix? So we can use this simple formula that rho of t equal to this unitary matrix, evolution matrix times the density matrix at t equal to 0 times the uh, conjugate of the evolution matrix. But that is a bit complex, and if you are doing a computation, it can take some time. An easier method is by utilizing the fact that that the density matrix is in the mass basis and the Hamiltonian is diagonal in the mass basis. So let us look at the derivation of some result that we will be using. So this is rho of t, which is given by this formula. Now let us look at an element. So this is a matrix, and the ijth element of the matrix can be obtained by putting a bra at the left and a ket at the right. And then you get this expectation value here. This is not an expectation value. This is a matrix element. So to evaluate this, we just uh, introduce this complete set of mass eigenstates and we add over it. So I have introduced a set of states between e to the power minus iht by h bar and rho, and another between rho and e to the power plus iht by h bar. So here you go I dash and j dash, and I have to sum it over I dash and j dash. Now look at the first factor over here. These I states are the different mass eigenstates, and this Hamiltonian is diagonal in the mass eigenstates. So if you apply this on the I state, it will just give you EI, where EI is the ith element, ith energy. So here E1 is P plus M1 square by 2P, E2 is P plus M2 square by 2P, etc. So that this factor comes out to the left, and this fact from here we get a factor. So just replace the H here by EJ. So you get this factor here, e to the power. Sorry, there should be an I before this E. So you'll get e to the power plus I EJT by H bar. And this I bra I with the ket I dash will give you a delta function here, Kronecker delta. Similarly, the bra J dash with ket J will give you another Kronecker delta. And if you sum over I dash and J dash, you will get this simple expression where the ijth matrix element of rho at time t equal to the ijth element at time 0 times this factor. So this is the energy difference between the two eigenstates I and j. Now let us look at the results here. So previously we could start only with pure electron, muon or tau or neutrino states, but here we can start with the mixture. So first we look at the ratio 1:1:1, and the density matrix will have all the three diagonal elements equal. Now, so it is proportional to the identity matrix because I'm assuming that there are no off diagonal terms here. And I multiply it by a factor of 1 by 3 because conservation of probability says that the total sum of the probabilities must be 1, and hence the trace of the density matrix must also be 1. Hence this factor of 1 by 3. And I run the algorithm in a code and get the results. So this is just a straight line, which means that it doesn't evolve at all. It just remains the same. Now this is very similar to unpolarized light, and I'll call it an unpolarized flavor state because it is statistically the state with the highest entropy. So, you know, state with the highest entropy is the most stable and hence it doesn't change at all. Or we could begin with some other ratios. Say we start with 50% mu, 50% tau, and 0% E. Then you can see that a similar kind of oscillations take place here. Or you could start with other combinations. Now, I'd like to remark that density matrix approach, as you can already see, is far more general than the wave function approach because you can apply it on mixed states as well. Now, if you look at this graph on the left, I have used the initial density matrix as it was a diagonal matrix with the first diagonal element set to 0 because nu e, the probability was 0 at first, and the rest two diagonal elements were set at half. So we got this graph. But here it is the same diagonal, but there are some new off diagonal elements here, and it has to be symmetric because uh, rho must be a Hermitian matrix. Now I have added this factor of half here in the diagonal, and you can see how this graph changes. The initial state is the same. It is 0% electron neutrino and 50-50 mu1 and tau1. But the evolution pattern is different here, and that is because of something called the correlations between different flavor states. The correlations are actually measured by the non-diagonal elements of the density matrix, and they can give rise to interesting patterns here. So instead of putting half here, you could have put any complex number. Just make sure that uh, this matrix is Hermitian. Now, that's all for today. You can have the code here. I'll send this to the main group so you can access the same code and run your own simulations there. Thank you.
Thanks, Souradeep. Anyone has any question or anything to say? Okay, then that's all for today. Thanks, Souradeep, for this talk, and thanks everyone for attending. Goodbye.
Bye.